In this video, we're going to be calculating with Avogadro's law, going through some gas law problems with stoichiometry, and finally doing some ideal gas calculations. So let's start here. What volume does 0.0685 moles of gas occupy at standard temperature and pressure? So remember, at standard temperature and pressure, all gases will have a volume of 22.4 liters. So I'm going to convert that using my standard little analysis here of 1 mole to 22.4 liters. So I take 0.0685 moles, and I'm going to use dimensional analysis. I'm going to moles on the bottom so that it cancels out. 1 mole, 22.4 liters. That's going to work out to here of 1.53 liters. So I just multiply this times that. So that's simple analysis right there, depending upon what I need to cancel out. So I'll put that up there, and I'll try another one here. How many moles of gas are in 2.21 liters at standard temperature and pressure? So I'm going to use the same idea here. In this case, though, I'm going to reverse it. I'm going to have liters on the bottom because I'm looking for how many moles. Liters will cancel out, leaving me with 0.099 moles of this particular gas at standard temperature and pressure. Remember, it only works for that. Okay, now I'm going to be taking this equation here. Propane and oxygen react together in this equation here. What will be the volume in liters of oxygen that I need for the complete combustion of 0.350 liters of propane? And we're going to assume that we're at standard temperature and pressure because it doesn't say any different. And we're going to try to figure out how much CO2 I'm making. So 0.0350 liters of propane, and so I'm going to use this dimensional analysis. 22.4 liters is going to be equal to 1 mole. I could go right here and just cancel that out, and that would tell me how many moles, but really what I'm looking for is I want to know how much oxygen goes with that. So I'm going to use my mole ratio here. 5 moles of oxygen for every 1 mole of propane. Just like I've done with other stoichiometry problems, now I'm just going to be doing the conversion here. And I know that for each mole of oxygen, that is going to work out to be 22.4 liters at standard temperature and pressure. Everything here is going to cancel out, just like we've seen in previous ones. Liters of propane cancels out. Moles of propane cancels out. In this case, moles of oxygen cancels out, and I'm left finally with my 22.4 liters of oxygen. One thing that you'll notice, I have 22.4 liters in both the numerator and the denominator. In that case there, I could essentially cancel those out because that's going to work out to be 1. So now I'm just taking 0.350 times 5 to figure out what I need for oxygen. That works out to be 1.75 liters of oxygen will react with all of the propane. All right, hydrogen and oxygen are going to react together in this equation. What volume of hydrogen gas will be needed to react with 4.55 liters of oxygen gas? What volume of water will be produced? So I have my 4.55 liters of oxygen. I know that 22.4 liters per mole, so I'm going to use that to figure out how many moles of oxygen I have. Now I need to get to hydrogen, and we know that for every 1 mole of oxygen, we have 2 moles of hydrogen. So I'm going to put 1 mole of oxygen down there, 2 moles of hydrogen up here. Now we need to convert that back into liters, and we know that for each mole of gas at standard temperature and pressure, that's going to work out to be 22.4 liters. Same idea there. Those are going to cancel out. Liters of oxygen cancels, moles of oxygen cancels, moles of hydrogen cancels, and 22.4 liters here and 22.4 liters there is going to cancel out as well, leading me to 9.1 liters of hydrogen gas is going to be produced. Now the follow-up question is, what about water? Well, fortunately, these ratios work out the exact same. For every 1 mole of oxygen, you have 2 moles of hydrogen, or 2 moles of water is going to be produced. All I really need to do is add on the oxygen here, and the math is going to work out to be the same. So at 9.1 liters of hydrogen, I'm going to end up with 9.1 liters of water, just because they happen to have the same coefficient. With the ideal gas law here, I'm going to use PV equals nRT. I'm going to be writing out all those different parts here. Pressure, volume, number of moles, R, and T. First one I'm going to do is I'm going to write out R. R is 0.0821. You don't need to memorize that. I will always give you that. However, if I'm going to use this value for R, the volume needs to be in liters, the pressure needs to be in atmospheres, the number of moles needs to be in here. I can't use grams, and the temperature has to be in Kelvin. If stuff isn't like that, I need to convert it to make it that way. So my pressure is going to be my unknown. That's what I'll be solving for. My N is going to be 0.5 moles. It's going to say 0.5 mole sample of nitrogen gas. My volume is going to be 10 liters, and the temperature is going to be 298 Kelvin. Now I can derive what I need. So my pressure is going to be the unknown. Pressure is nRT over V. I'm solving for that. Now I can plug in the numbers. 0.5, 0.00821, that's R, 298, and divide that by the volume of 10. That's going to work out to be a pressure of 1.22 atmospheres. Remember, to use this value of R, I need to make sure everything matches there. So let's figure out what volume of methane will be occupied by this many moles at standard temperature and pressure. R 0.0821, standard temperature and pressure, that is 1 atmosphere and 0 degrees Celsius, but I have to convert that to Kelvin in order to use R, that's 273. So there's my temperature, there's my pressure, and my number of moles is going to be 0.0035 moles. Now volume is going to be the unknown, so take PV equals nRT. I'm going to solve for volume this time. Plug in all of my numbers, divide by the pressure, and I'm going to get 0.0784 liters. If I was to convert that in milliliters, that'd be 78.4 milliliters. 4.44 liter container holds this many grams of oxygen. Here's my first red flag. I need to make sure that's moles of oxygen, not grams, and this temperature here is in Celsius. That will need to be converted into Kelvin. PV equals nRT. Pressure is my unknown. Volume 4.44 liters. That matches R. That's okay. R going to be 0.0821. I'm going to use that, so I'm going to have to convert stuff. 22.55 becomes 295.55 Kelvin. And my N is I'm going to have to take this grams of oxygen and convert that into moles. And we know that 32 grams of oxygen from the gram molecular mass is going to be equal to 1 mole. That's going to work out to be 0.481 moles of oxygen. That's what I'm going to put here for N. I can move this out of the way and can continue on with the rest of my equation. In this case, pressure will be the unknown. Solve for everything else here. Divide by volume. That works out to be 2.63 atmospheres of pressure. Solving for all that stuff, just remember to make sure if they give you grams, convert that into moles. All right, 500 grams of helium are held at standard temperature and pressure. What's that volume of the container? So PV equals nRT, standard temperature and pressure, 1 atmosphere, 0 degrees Celsius, but has to be in Kelvin. 273 Kelvin, so I can put those in there, 1 atmosphere, 273 Kelvin, 0.0821. I'll use this stuff here. What I'm going to be looking for is volume. So my volume is going to be the unknown, and I need to convert 500 grams of helium into moles. I know that 4 grams of helium is 1 mole. Canceling that out is going to give me 125 moles of helium. We'll move this out of the way, and now I'm going to be solving for the volume of that container. nRT over pressure, add in all of my units. And when this all shakes out, the volume of this container is going to be 2,801 liters. It's a very big container, but 500 grams of helium is quite a bit right there. Helium is a very light, not dense gas. Need a lot of it.